So Qiang is from University of Bielefeld, Germany, and as mentioned by Nathan in his talk, so Qiang has pioneered in the tactile servering, and let's welcome Qiang for his talk.
Okay, thank you for your invitation that I can have a chance to discuss so many famous guys in tactile domain. So it's nice I can meet them and to learn from them. And also right now, Mason talking about the tactile serving. So I'm also quite happy to explain more detail how my tactile serving works in my scenario. It's quite similar and also nice to see the both direction line parallel running. So let's see what I'm doing now. So, but unfortunately, right now, Kaspar showed a very nice picture, which is published in our IROS paper in 2018. I didn't explain that in this talk. That's a way to combine the vision and tactile, but I will give more basic idea. I mean, what's the fundamental thing to combine the vision and tactile in this talk? So in that hope, everyone can understand more detail on the principle side. Okay, first I need to share my slides. Okay, can you see? That's good. Okay, thank you. Hello everyone, my name is Qiang. I'm from Bielefeld University, and today I want to talk about the intelligent tactile robots. So the agenda for my talk today is quite simple. First, I would like to introduce what's the tactile information, what I mean. So, because from the Professor Bilat, she gave a talk, also mentioned this concept. I think maybe I can give some complementary information regarding this terminology. And the second one is, if we have this information, how we can use it for the robot manipulation task. So that's the two thing I want to talk about today. So as recently we can see a lot of applications in tactile robotics domain. For example, in medical robots, it can take care of our human, even lift our human. And also we can see some robot has been used in the kitchen scenario to help us cooking. So that's quite nice for lazy people. And also we can, several years ago, we have seen this DARPA challenge task, for example, this rescue task. We also can see robots can use the tactile sensing to do a lot of complex tasks. Finally, in the industry domain, we can see more and more collaborative robots available, which can help us to do the more complex tasks in unstructured environment. So that's bring me question. I mean, I want to understand what's a common research point behind. So my answer is I found that many commons is this robot need to contact with the real world. In that case, tactile information is really, really important. And in that case, I also work with my other colleagues to organize several workshops in humanoids and also IROS aircraft several years ago. And we discuss how tactile can be used for manipulation, for perception, and also for the real application, for example, assembling. And also we want to bring how tactile can be connected with skill, I mean the manipulation skill. So we also discussed a similar thing before, and we get some conclusion. I would like to share this conclusion with all of you. First one is my opinion is it's good time to bring the concepts I would like call the tactile robotics available. Why? Because we see now tactile sensing becomes more and more used in the robotics domain. So this is a growing area. And in this research topic, it normally is covered three directions. First is a hardware designing, the hardware tactile sensing. The second one is how we can use the tactile sensing for perception. So this is a perception from robotics called perception. And then if we can see something, we can feel something, we see something, and then we feel something. And then we want to control, we want to do the reactive control, we want to do the deliberately control. So there are three topics are involved in the tactile robotics. And also I'm thinking about that this tactile robotics is not starting from the beginning because we have very good basis, theoretical basis. For example, we have a very nice mathematical manipulation theory to support the tactile robotics. And also recent years, we can see more and more machine learning technology are used for tactile sensing processing and even for the tactile control. So this two-pillar theory supports the tactile robotics. And in that case, to this end, I quite believe that this tactile robotics can empower robots with a higher robustness in a real-world application. So this is my vision. I mean, I think it's time to bring our energy together to discuss about this direction. And okay, it's very fantastic, it's promising, but I also can see different problems. First is from sensing aspects. So now a lot of tactile sensing available, but I'm thinking about a lot of them are still using the low temporal and spatial resolution. So yeah, definitely there's more and more new technology and new sensing available. It's an ongoing project. So that's why I say this is an unsolved problem. It's still challenging for us from the hardware sensing side. Second one, we need a processing method for perception. So even you either use the model feature based or use machine learning method to automatically extract this feature. And third one, we have this feature. We need to use this feature in the control framework. And think about more robust control framework will be also helpful for improve the tactile manipulation capability. So this is the challenging side we get from the discussion in the previous workshop. And other output from workshop is also includes several other three things. First one is in 2020, I worked with other colleagues from CMU and also USC, Stanford University, Darmstadt, and also TUM to finish one TR paper which summarize what kind of feature can be extracted. So that's why I call tactile information. I'll explain more detail about this information, what it means. And then in 2018, our workshop output is there is a special issue in IGHR. It's only care about tactile sensing for the manipulation task, for grasping and for in-hand manipulation, etc. And recently, I also worked with Sun. We are working on Elsevier edit book. We invited many researchers who working on a similar domain and to show the state of the art. And hopefully this book can be available in August or December or September. So let's see. Okay, and first I want to show what raw data we can get, what we can directly get from the tactile sensor, available tactile sensor. This includes normal and tangential force, and vibration, thermal, and pre-touch permissivity. So this is somehow covered our human finger capability. So this is the raw data from the sensor side. This is raw data. And tactile information I want to define here is a unified representation for perception and control. Why I call that? Because I mean there is also continuing domain. So somehow we separate with control and perception. But in other way, I would like to argue that perception and control information both are computed. So they can be unified in the computational framework. That's why I'm considering the interactive scenario, and we define the different level this information which computed from the raw tactile sensing. So the first one is a contact level information, and accumulated the contact level information is possible to estimate the object level information. And we need to use action in order to extract object information, or we need to compute the tactile action level information for decision. So that's the three layer in the computational framework to define, we call the tactile information. Contact level information, that's the basic information which can directly from the raw data, which includes contact geometry, force and torque, contact events, and also material property. So that's our summary about the information which is related to contact level. And object level is where the object is, object localization, and what's object look like. This is somehow we consider about that from the geometry side. So it's a roundish, it's a cube-like. So this, what's the geometry information? And also the mass and dynamics, like Lorenzo talked about this grasping thing. So we need to think about how about the mass and dynamics information for the object in order to we can dynamics control the hand for stable grasping. And also one thing not care about too much until now yet is the content of container. What's that? That's somehow, for example, we have this bottle, and in bottle there's water inside. So we quite believe that we can use the tactile information to extract the information about inside things. So that's the information we want to extract from tactile, because this information is very difficult from extracted from the vision. And finally, what's the action level information? Action level information includes the discrete decision for action and also continuous decision from the controller. I want to use a grasping as example to explain the action level information. For example, let's say action selection and initialization. This means we're assuming that we have some grasping experience, tactile experience. We collected this tactile experience. We can compute action posture to say, okay, in this posture, in this tactile pattern, we can stabilize grasping object. So this initialized the grasping posture. This is the first action, we say this action level information. Second one is, once robot use its hand grasping the object, and robot should use a online mirror tactile information to reactively computed the control variable, the motion of finger, in order to stabilize the contact. So that's I call the reactive controller. And then action determination. What does this mean? So in some situation, because right now, example is the slippery detection. Okay, you see? So there is a slippery detection is decided. So robot should stop its current controller to switch to another one controller in order to grasping the object again. So that's I call the action terminate. So action, you should use tactile information to determine the unexpected events. So this is action decision also. And finally, the robot, for example, want to do the inclination. The robot need to stop at the goal posture of the object. So that's why robot use the tactile information to do that, also to decide whether the task has been finished or not. And also final one for action output verification, what does this mean? This means when robot grasping object, and we cannot evaluate whether this grasp is stable or not. So that's why robot need to take external action, for example, lifting to decide, use from tactile information to decide, okay, now it's stabilized grasping. So that's why I say we need to take the another action level information is another action to justify whether the previous goal has been achieved or not. So that's the different level information. And how we can compute this information. I mean, this is a thing, the difference. So there are two ways we can do. First one is a physical model-based technical information computation. I mean, this is mainly I will talk about in the following maybe 5 or 10 minutes. And another one is use a pure machine learning method. For example, use a data-driven approach or maybe imitation learning way to do that. So that's also possible. So using the physical model-based tactile information, advantage is, as a designer or a programmer, we can understand the whole data process. So we can know robot will do the horrible things. For machine learning, I mean, recently we can see a lot of work on this direction. I'm also watching this direction and also hope we can bring these two things together. Advantage for machine learning thing is we do not need to understand the feature. but the perception and also the control, it works. So I would like to see in future, somehow these two directions can be merged in future. So there are more detailed discussion about the lot of recent work in the journal paper, in the TR paper. If you are interested in this class, in the catalog about the tactile information and applications, I would like to encourage you to read this TR paper in last year. And with the next several minutes, I will talk about my application using the tactile information. For example, for the tactile exploration work, and also in-hand manipulation task. So first is the tactile exploration. I will introduce the tactile sensing we are using. This is a picture resistive sensor. It's a plate sensor, and 16 times 16, 2 kilohertz, and spatial resolution is 5 millimeter. We can use the tactile image-based method to extract a lot of contact level information. For example, contact position and also the line feature. This is, I call it contact level information. So that's quite easy. We can use a tactile image to do that. And we also do the calibration to evaluate this tactile sensor. We also do the calibration. How this calibration is done. So we have the square sensor. You see this 5 centimeter times 5 centimeter. And we use a probe to touch the every texel. So this can provide the ground truth where the probe is. And then we use the tactile imaging method to compute the contact position. It's amazing thing we can see finally is, although our tactile sensor physically, we have 5 millimeter spatial resolution, but after this computation from the image moment method to compute the contact position, the spatial resolution can be higher up to 0.5 millimeter. So this impresses us a lot. To this end, we propose several methods for using the tactile sensing for calibration. If you are interested in this work, you can think about reading the paper, our humanoids paper in 2016, and also the in 2015 also in humanoids, to how we can use a self-touch to or contact to close the kinematic chain in order to improve the kinematic chain model for fine manipulation with only tactile sensing capability. And we not only calibrate the contact position, we also calibrate the line feature. We found the image moment computed method is better than pure image computed, like for the half-line compute. The line feature we use image moment method is better. And now we have the contact level information, contact position, and the normal and the line feature. How we can use this information to compute the action level information, which I say this is relative control. So that's the solving. So this is mapping from somehow mapping from the sensing to controller. The idea behind the tactile solving is now we have a very rich tactile feature, and whether we can design a control framework which can implement different tactile related primitive tasks, and then we combine this primitive task can implement more complex tasks. So that's the idea of the tactile solving framework. So we do not only for specific task, but we want to define the framework for primitive task and then can be accumulated as more complex task. The idea we are doing is like this. So we want to implement task is let the robot assemble tactile sensor, this square sensor, to exploring and or you can call it interact with unknown object. And we can use the tactile contact information as a feedback to use a closed loop to safely interact with the object. The idea what we need to do is always maintain the contact position in the center At the same time, we can generate some forward motion along the robot end effector frame, and then we combine this task together can form more complex task. So the idea would be if we want to maintain the contact position in the center, and in that case, in the tactile space, there will be a deviation. This deviation will be projected by an inverse Jacobi matrix and to generate the robot end effector motion. And this motion will be combined with a forward motion from end effector to generate more complex task. And I would like to use the demo to explain how this works. It looks like I'm late, but I will try my best. So this is a framework, tactile solving framework. And first I will explain the primitive, how it's implemented. Let's see. We're using the framework can do the sliding motion. You see, if there is a sensor, if there is a tactile image deviation, and robot will directly moving to the center. And then using this primitive, it can generate more complex tasks to following the pen motion. And not only we can control the sliding, we can also control the rolling. With the sliding and also the rolling, combine these two primitives, we can do a little bit more complex task. Let's see with the following video. This is control the twist. Right now it's control the pitch and yaw. This is control twist. Its goal is maintain the contact, this line feature in the center of the in the along one axis of sensor frame. And these three are primitives. Sliding and rolling are primitive. And we combine this feature for tracking one unknown cable. So what we did is always according to the current measurement on the normal direction, change the twist. At the same time, robot generate a forward motion. In this case, it can follow a cable which is unknown. The curvature, everything information is unknown for robots. So this is a work published in 2013, as mentioned right now by Nathan before. And also we can use a similar idea to covering this unknown shape of the bottom using the tactile solver. The idea is always maintaining the contact position in the center by rolling, at the same time generate the forward motion of robot end effector. And I want to say this work can not only used by used by the square sensor, but it also can be used as a fingertip sensor for the this is how to say concave curvature exploring. So right now explain the tactile control framework is below that. So the output from this control framework is the end effector motion of robots. And the tactile channel can be combined with the vision task related servoing task in the to generate the composited sensor output to generate the motion for the visual tactile servoing. This is this framework. And time issue, I just show this video, let you know how this work can be done. So this is somehow combine the vision and tactile in the lowest level to combine the vision tactile for servoing. For example, this is for grasping, just using vision to attach object and sliding for the better grasp posture. And then using, because if we're only using the force, and this is not well calibrated force feedback sensor, and we can use a vision on top of it to stop that is localize some posture, not moving anymore. And then we can say we can use a vision as a feedback to guide the robot change the posture of this box. And we want to argue that this method not use the cylinder object, but other shape object also. And this is for the tactile exploration. Combine the vision and tactile, we can get the visual tactile point clouds, and this point clouds register the contact point in the object frame. So it's can be used for a lot of classification or other tasks. So I think I'm running my time, but I would like let this video is finished. Sorry for that, Simon. Maybe next time I can share other things.
Okay, sorry, we're running out of time.
It's okay, it's okay. I can understand.
Okay.
So because I previously I want to somehow like rehearsal my talk, but right now there are too many fantastic talk. I do not have chance to do that.
Okay.
So this is.
Shall we go for some quick questions?
Yeah.
Any questions from the audience?
Mm-hmm. So this is you can think about this two finger to rotate the object, put on the table.
Okay, I will ask my question now quickly if there's no volunteer.
Yeah, please.
Okay, so you have this dual arm setup and you have visual tactile control, and I believe you have a latent space for vision input and tactile input. Can you please give us more details how you combine them in this latent space?
You are right. So our tactile sensing is running in, in the real setup, we're running in 500 Hertz. So the robot control in 250 Hertz and vision in 30 Hertz. For the manipulation task, we somehow reduce the time, unify the time in the vision in the vision frame. So which means we control in 250. But the feedback coming with coming with the 30 Hertz.
Okay, I see.
So we somehow we lose some information from the tactile domain. So from the tactile feedback.
Okay. Mm-hmm.
In order to unify them in a framework.
Okay, I see. Okay, any other? Okay, Nathan.
Oh, thanks. Sorry, my raise hand feature doesn't work. So, because I've started working in server control now as well as you know. I was wondering, to pick your brain, what do you think are the important directions to take tactile server control forward? What's the kind of big outstanding problem? So
yeah, that's a very good question. I mean, actually. Professor Billard has done something before. So in her talk, he showed some tactile exploration, right? So in his tactile exploration is not only using the fingertip, but also the link. And even something, I don't know whether they are using palm. But from my side, I would want to go in this direction. Next step is I want to use a whole hand for grasping, not only use a fingertip for grasping or inhalation, but I want to exploit the capability of the link and also the palm in the planning or learning framework. So that's the thing I want to in future I want to do. Right now, I do not have time to share the some work I done several years ago for inhalation, but the idea will be extend the previous in-hand manipulation with the link and the palm. I think that will be the very interesting work direction I want to pursue in the next years.